Well, that cough, you're probably going to hear a lot more of that. Let's talk about analysis of variance. And we're going to briefly review what we know about one-way analysis of variance before we dive into factorial analysis of variance. So remember, in analysis of variance, you're comparing two or more groups, but in this class we usually say you don't really need it unless you have three groups. And the trick to comparing the means of more than one group to each other, more than two groups to each other, so three or more, by using variance, is that you get an estimate of how far apart any given couple of points should be from each other by looking at all the within group variance. So that's an estimate of how variable data points are just in general in your data set. That's an estimate of population variability, random variability that just exists. That would mean within group variance. And then you compare that to the between group variance. So if the within group variance is small, but the means of the groups are very far apart from each other, then those groups will have really separated means and kind of concentrated distributions in themselves. And you can be pretty confident that the differences between your means and your sample are probably representing something from the population. And the way we know that, or the way we express that, is saying the between groups variance is pretty big compared to the mean, to the within groups variance, the average within group variance. So if there's a lot of overlap between the groups and there's a lot of within group variance and not very much between group variance, then you don't really have any confidence that the group means are different from each other in the population. Of course they're different in the sample. Everything in the sample is different. There's always some kind of a difference in the sample. So we calculate the between groups variance, and we treat each group mean as one data point. We make a variance from that, and that's the mean square between. We calculate the average within groups variance, and that's the variance for each group, and then we average those variances together, and we have the mean square within. Now, the way we get these variances is a bit of an odd process. We use the mean square and the sum of squares and stuff like that. But in the end, we have these mean squares, and it's just variance. It's just between groups variance and then average within groups variance. And that within groups variance is our estimate of random variance, sometimes called residual, sometimes called error, something like that. It's variance that's not accounted for by the factors in the study. Sorry about all the coughing. This is bad timing. So to use the F ratio, in other words, to do an analysis of variance, first of all, we need a comparison between means. The data have to be interval level, so they have to be numeric, not ordinal. In general, you should use random sampling, but all that really means is that if you don't do that, then you have a more difficult time generalizing beyond your sample, which isn't really the same as saying you have a difficult time talking about differences among your means, because that's kind of separate, right? External validity. And you need a normal distribution in each of your groups, but approximately normal is okay, partly because of the central limit theorem. You also assume equal variances, and that's kind of a big deal. However, if the variances in the groups are only different by a factor of 2 or 3, then it might not be such a big deal. If it gets bigger than that, you might have problems. The sum of squares is the core of this whole process. It's the sum of the squared deviations. And that's the core of any variance calculation as well. That leads us to our first quiz question. So if you don't have your quiz open, now's a good time to open it, or you can come back to this video and redo this as many times as you like. But the first question in the quiz is, what is the sum of squares of a regular variance calculation, like a single variable? Just a regular calculation of variance, as if you were calculating the variance of a few numbers that were just one data set. So moving on, here are the answer possibilities. And I'm going to move on. You can choose these for the quiz. And so let's remember one example we did to demonstrate how analysis of variance works. We wondered about how many children a bunch of people who were Democrats, Republicans, or Tea Party members might have. It was a ridiculously small study with only 3 participants in each group. So just for demonstration purposes. So you can talk about the deviations from their mean and calculate the variance and calculate the grand mean. You don't really need to know all those details necessarily, but graphically this is kind of how it looks. You've got the Democrats, and then one had 0 children, one had 1, and one had 2. The mean of that is 1. So the mean of the Democrat group is 1. And you can talk about the deviations from the Democrat group. A deviation of -1, a deviation of +1, and a deviation of 0. The sum of squares for Democrats is 2. So the sum of the squared deviations from the Democrat mean. The Republicans were more spread out. There was one who had 2, one who had 4, and one who had 5. I made up this data, so it's shameless stereotypes, probably. So you get those deviations, and you square those deviations, and there you go. 4.67. That's the squared deviations from the mean for Republicans. That's their sum of squares for Republicans. And then the Tea Party members, they were spread out as well, maybe even more than everybody else. And you get those deviations. Those are 8, the largest number of deviations. So the sum of the squared deviations there is 8. So that's the within groups sum of squares when you average those things together. You add them all together, and that's the sum of squares within. You divide it by the degrees of freedom of each group, and then you get the estimate of within group variability. So then there's the between groups variability, where there are just basically 3 data points, one for each mean. So you've got a data point here, and a data point here, a data point here, and then the grand mean of all the data points, and you look at the deviations from that. So the sum of squares between is 11.56. Kind of a small sum of squares for between, large sum of squares from within, but we still haven't seen what happens when we divide by n. And then sometimes we calculate the sum of squares total. It's not actually an important part of analysis of variance. It's something we used to do when we had to do stuff by hand to check our work, because between and within will add up to be total, as you see in this example here. So the sum of squares by itself isn't a good measure of variance, because you have to kind of average things out and find out variance per individual, just like our variance calculations, which is sum of squares divided by n, or divided by n minus 1. Well, we kind of have to do the same thing. The mean square is the mean sum of squares. It's a variance estimate. And we have these formulas, which you don't really need to know, but this does explain where things come from. And so once you have your sum of squares and your degrees of freedom, which is essentially the kind of like n, then you divide each sum of squares by the degrees of freedom, and you get the mean square. And now we have variance. Mean square is variance. It's an estimate of variance. So in this case, we see that between is bigger than within. So the estimate of the variance between groups is bigger than the estimate of the variance within groups. We have these 2 different kinds of variability estimates. The F ratio is dividing the mean square by mean square between by the mean square within, which shows you how much bigger the mean square between is than the mean square within. You want it to be a lot bigger, of course. And F is the sampling distribution that we use to figure out if that's big enough. So we look at the F distribution that is all the different sampling distribution rate or sampling ratios like this, mean square and between and within ratios that could have happened with these degrees of freedom if the null hypothesis is true, and if there's no actual difference between the means and the population. And if our result is way out in the tail of the F distribution, that means that it's very unlikely that we would have found a ratio between and within that's this big if the null hypothesis was true. So we would conclude that there are some differences between the means. Differences that can't be explained by just random variability, which is the within part. I'm just going to click this and keep moving. So now we have question 2 in the quiz. What would an F ratio of 1 mean, of exactly 1? I'll pause here. You can pause as long as you want. I'm going to move on. The Anova table is how we figure out what happened in the analysis of variance, and those pieces all have interesting things to say. But for this class, we're mostly concerned with just identifying the source of variance, whether it's between groups variance or within groups variance. Sometimes we're interested in the degrees of freedom, and then looking at those mean squares, but we only care about those because we divide between by within to get F. And we only care about F to find out if P is less than 0.05 or 0.01 or whatever we've chosen for our alpha level. So when we're doing things by hand, we only can figure out if p is less than 0.05 by comparing our observed f to an f critical value. Now, we don't even have an f table in this class, so just be aware that that happens. In this class, we'll use a computer. So in this particular instance, we find that p is 0.18, which is definitely bigger than 0.05. So we do not reject the null hypothesis. The null hypothesis is that the means are actually the same in the population. The mean of the Tea Party, Republican, and Democrat numbers of children are the same. We can't reject that. We don't have enough evidence to reject that. So a significant F ratio tells us that the means are not all equal to each other. Now, we're not talking about sample means. We're talking about population means. The significant F ratio tells us that our best guess is that the means are not all equal to each other. So we accept currently, for a while, the hypothesis that the means are different in the population. And the long version would be something obnoxious like this. Now, going back to our conceptualization of within group and between group variance, reminding ourselves of what we're doing here. Let's look at question number 3. What is the mean square actually a measure of? So see the quiz on Angel for the options to answer this question. Moving on. So a significant F ratio doesn't tell us if there's a statistically significant difference between any particular two means. It just tells us there's a difference overall, as we've talked about before. To find out if there's a difference between two specific means, we need to use a t-test. However, as we've seen, that there are problems with doing a whole bunch of t-tests. The family-wise error rate, the family-wise type 1 error rate, alpha family-wise alpha. So sometimes we do these unplanned comparisons. In other words, we just compare everything to everything else. These are called post hoc comparisons or post hoc tests. Post hoc has kind of like a bad name in statistics. It sort of means that you're lame and you didn't plan your study well enough, or you found nothing, so now you're fishing for some kind of results. And as you can imagine, that's problematic. Just by random sampling, you'll find some things that don't exist in the population but do exist in the sample, and you're more likely to find those things if you just start fishing around. So we try and prevent that by doing only planned comparisons, but we have other ways that we try and do it as well, like correcting our alpha for family-wise alpha error rate by using something like Tukey's HSD or LSD or something like that. And we also use the F ratio as a gatekeeper. So we prevent ourselves from doing too many tests by refusing to do any of these means comparisons unless the omnibus F test, the overall F ratio, is significant. So post hoc comparisons are when we make comparisons between multiple different pairs of means, two means at a time. Anova always has, well, Anova usually has 3 or more, but we can do it just between all the different pairs. Post hoc tests. Now, Tukey's HSD test, honestly significant difference test or procedure or whatever you want to call it, is a way that you just kind of after the fact correct those tests. You just do a bunch of t-tests and then you correct them so that your family-wise error rate is correct. What that correction means is it just makes it much harder for you to find significant difference. You need to have a much bigger difference between any two pairs of means than you would with a regular t-test before you're allowed to conclude that there's a significant difference. So we control family-wise error rate actually in 2 ways with Anova. Number 1, using F as a gatekeeper. We don't do any pairwise tests unless the F ratio is statistically significant. And that can be painful because we can look and say, oh my gosh, but group A and group C are totally different. But we stop and say, not significant, we're going to stop. And then even if F is significant, then we're cleared to go ahead and do pairwise tests if we want to look like Schmiels. And we handicap those results using a separate procedure. A post hoc procedure like Tukey's HSD or LSD or Chaffee test, a Bonferroni test, something like that. So post hoc pairwise comparisons. First, we do the one-way Anova. We ask if the F is significant. If it is, then we find all the differences between the group means. Now we can conceptualize this with a k by k matrix. In other words, k is the number of groups, so number of groups by number of groups. And when we look into these differences between means, it's helpful to just look at the absolute value of each paired mean difference, because often the procedure used, like Chaffee test or HSD or LSD, will just say any mean difference of this big or bigger, like absolute value of this big or bigger, is significant, and anything smaller is not significant. So having this matrix of absolute values can be really handy. And then you have to keep track of which of those differences was positive or negative. In other words, which mean was bigger than the other mean. So it's helpful to keep looking back at graphs and things like that. So then you do the correction, which isn't that difficult, but it's easier to just check the boxes in the computer. You'll have fewer calculation errors, and it's more fun. And then you look and see what's significantly different from what, and you try and interpret the results. That's where you can get stuck. So you have to be careful which tests you do, because sometimes you do tests that you can't make good on because you can't interpret them. So here's an example: the performance of 5 memory strategies for remembering words. Here we see the means of the memory strategies. The memory strategies are counting, rhyming, using adjectives, using imagery, and then intentional memorization. So here's the Anova table for that. We can see that the F test is significant. P is less than 0.01 for F. So if our alpha was 0.01 or 0.05, then we're significant, and that's okay. So now that means we can do post hoc tests, as long as we correct for family-wise error while we do them. So here we see all 5 means with their number of subjects in each one. And we can do all of these comparisons, but we need to get all the cell means, because that's what we're doing comparisons on, the cell means. All n's are equal here, which is kind of nice in Anova. It makes things simpler with the math. It makes the results a little more plausible in some cases. So if we look at all these means, 7, 6.9, 11, 13.4, and 12, and we list them against each other in a matrix and only take half of the triangle of that matrix, then we can see how many comparisons there are and we can look at the differences between those means. So the difference between 6.9 and 7.0 is an absolute difference of 0.1. 11 and 7 is 4. 12 and 13 is 1.4, etc. Absolute values, positive values only. And we don't use the diagonals, because it's a mean with itself, which will always be 0, and that's silly. And there's redundancy. The lower triangle and the upper triangle will have the same values, sort of a mirror image of each other. So we just use one triangle. Doesn't matter which one. So the software is going to tell you which mean differences are statistically significant. It might or might not give you a nice matrix like this, but I think the matrix is still nice to help you focus on what's going on. So in this case, the software tells me that there are 4 significant differences. You can kind of see that there's sort of a rule, like, I don't know, 4.5 or 5 or bigger is going to be significant here. Everything that's bigger than 5 or 4.9, something like that. Anyway, those are the significant differences. So we can go back to the graph and see how that looks. So we can see that counting and imagery, the difference between those two is 6.4, the mean of the counting group, the mean number of words recalled there, and the mean number of words recalled in the imagery group. And that's statistically significant. So I can put a line and an asterisk there. Also, counting versus intentional memory strategy, that's statistically significantly different. So counting isn't a very good strategy, it looks like. And rhyming isn't so great either. So rhyming versus imagery and rhyming versus intentional. Now I notice that adjective has a value that's sort of in between the high values of imagery and intentional and the low values of counting and rhyming. And it's not different enough from either one to be statistically significantly different. Maybe if we had a bigger sample size, it would be, but we wouldn't know unless we tried that. So our conclusion here might be something like this. In addition to our omnibus F conclusion. So now question 4 in the quiz. When is it okay to compare all possible means? Once you're done with that, try question 5. In this example, with the memory strategies, what would be a reasonable planned set of comparisons? Not the post hoc unplanned ones that we talked about, but what if you did actual planned comparisons? Try and guess what would be a reasonable set of planned comparisons. And that's the end of that.